I'll give a progress report here on an observing program that I initiated about 5 years ago. And the goal of the program is to get stellar kinematics at the very centers of nearby massive elliptical galaxies and attempt to measure the supermassive black hole masses. And I would like to highlight the contribution from Nicholas McConnell. I just signed off on his thesis, and he'll be moving to the University of Hawaii for a postdoc next week. And today I would like to more focus on not just our observing program, but also the implications for black hole scaling relations. So when one talks about the scaling relations, probably this is one of the plot that has been shown in many, many talks of the mass of the black hole that have masses of the black hole that have direct dynamical measurements versus sigma, the velocity dispersion of the bulge of the galaxy. And this is from the Göttingen et al. 2009 compilation. And you can see there are about 60-ish objects here, but I would like to convince you that hopefully by the end of this talk that it's time to stop showing this plot because there have been so many updates in the past 3 years, and the slopes have changed too, and I will describe the progress our team and other teams have made in the past 3 years. And just to give some historical perspective, this correlation between M and sigma was first pointed out in 2 papers in 2000, and the 2 teams got different slopes. One was about 4 and one was about 5. And Göttingen's compilation gave about 4, and as I'll show you, now we're getting about 5. So our focus for the observing part is to focus on the very, very high end. If you look here, as of 2009, there are very few measurements in massive galaxies. And massive galaxies are very important, especially the very massive black holes. You can see 10 to the 10th is here. And part of the reason is because the connection to quasars. So if you look at the quasar mass function compiled from SDSS, of course here the black hole mass is not through direct dynamical measurements, but through line widths. So they are less accurate, but the power of this study is in the statistics. There's thousands and thousands of points here. And you see this general trend that black hole masses decrease. Black hole masses in quasars decrease when you go to lower redshift. Of course, this doesn't mean that black holes are losing masses, but rather the hosts where black holes sit in tend to be lower mass when you go to nearby universe. So then the obvious question is, where were the 10 to the 10 solar mass black holes? Here you can see some of them. Where are they today? And clearly, they're not sitting in active galaxies that's shining out like a quasar. So an obvious suspect would be nearby massive elliptical galaxies. So that's part of the motivation for us to go after nearby massive ellipticals. So massive galaxies, as you saw, tended to host larger black holes. Shouldn't larger black holes be easier to measure? Why haven't they been seen until sort of within the past few years? So there are at least 2 challenges observationally. One is you need to, obviously, to infer the black hole mass, you need to resolve the sphere of influence of the black hole. And but black holes, but massive galaxies are rare, right? The mass function decays rapidly at the high mass end. So to look at massive galaxies, you got to basically go beyond Virgo. And just for some perspective, Sora and Alice, the wonderful survey of early type galaxies, is volume limited to 40 megaparsecs. And we really need to go beyond that in order to just find massive galaxies. And the sphere of influence, a good number, rough number to remember, is given here. And this is the sphere within which we would like to get stellar kinematics in order to feel the black hole's gravity. And so say for a 1 billion solar mass black hole for a pretty big galaxy, it's about 50 parsec for the sphere of influence. However, as I said, we need to go pretty much to about coma distance, which is about 100 megaparsecs, before we can get these large sigma massive galaxies. So put 50 parsec at 100 megaparsec, you need to resolve about 0.1 arcsecond. So, of course, Sandy and others, the nuclear team, have been using HST to get such resolution, but very smartly, they focused on somewhat smaller galaxies for the following reason. Okay, so challenge number 2 for going after these very massive galaxies is that if you look at just the surface brightness profile in the center of these galaxies, the core ones, the solid curves, tended to be the more luminous, more massive, higher sigma galaxies. And the power law ones tended to be the smaller ones. So just to get enough signal to noise, to get the stellar kinematics for this part is extraordinarily difficult. Of course, it's an interesting theoretical question by itself that why core galaxies have, why massive galaxies have shallower surface brightness here. Some people believe maybe binary black hole, the slingshot ejecting out stars may flatten the inner core, but that's a story by itself. Observationally, this is a fact. If you want to look at the very massive galaxies, the surface brightness is very low. So HST actually isn't quite big enough. We need ground-based 8 to 10 meter telescopes. And then we also need HST type of resolution. So these two together made us look around, considering the instruments available about 5 years ago, to do a survey based on using ground-based telescopes, but also adaptive optics for some of the sources. Okay. So this is what, very briefly, what we have been using to get the black hole mass, to get the stellar kinematics. So we have relied on a number of spectrographs. Of course, nowadays with the availability of integral field spectrograph, it allows us to get a two-dimensional kinematics in one shot. And that's extremely powerful for for modeling the black hole mass. I'll mention briefly. That is, basically the more information you can get about the stars, preferably not just along the major axis, along a slit. If you can get 2D kinematics, it really helps to constrain the parameters much better. So we use a combination of Keck Osiris and also Gemini GMOS. This is seeing limited. And also we need somewhat larger scale kinematics to constrain the dark matter contribution to the potential. So we tried to get all of them. And as you saw, 1 billion solar mass at 100 megaparsec was 0.1 arc second. But we got lucky and we got 10 billion solar mass black holes at 1 arc second. So, so GMOS is actually quite useful. The seeing limited sum for very, very big black holes is actually capable of getting the kinematics good enough for black hole measurements. Okay, so for example, one famous galaxy we went after was the BCG, the brightest cluster galaxy in COMAT, NGC 4889 is this one. And so basically what we're doing is we put the IFU at the very, very center of these galaxies trying to get a stellar kinematics. Okay, so just to give you an overview of where we are, it's taken a while to get the telescope time, and as a prior theorist, it was just new learning experience, how patient you have to be an observer, to apply for telescope times, waiting for the weather to be good, and so on and so forth. It was painstaking. But anyway, so far we have published 5 black hole masses, and these 5, we first targeted BCGs, but now we're just opening up our sources to any massive ellipticals. And here are some of the parameters, and here are the black hole masses, and I'll show you a plot with error bars on it, and we've published these 4 detections, 1 upper limit, and 3 separate papers. And we have data in hand from a number of galaxies, and you can see the distances typically are beyond 40 megaparsecs. A few of these are in the southern hemisphere. We're using GMOS South. And these are the different combination of data we have. And for one in particular, we actually have 4 sets of IFU data. So we're very excited about analyzing NGC 910, trying to compare the kinematics. So let me just show you a couple spectra for what exactly we're trying to do. Okay, so what we're able to obtain, what we want to obtain, okay, and we were able to obtain, is the stellar velocity, line-of-sight velocity distributions. Not just the velocity dispersion or the radial velocity. We'll like the full velocity distribution. And to do that, for GMOS, we use the calcium triplet that we heard about this morning. And for OSIRIS, for example, we use COH band. And For virus P, it's more in the optical, and we were able to, here we show you the spectra from different regions of each galaxy. Okay? And basically, we convolve these set of template stars with some velocity distribution and find the best fit to the observed spectra. Okay. And we can get this for many pixels on the sky. Okay, so we have the velocity distributions for each galaxy at many spatial points. Now, very briefly about how we go about getting the black hole masses. Okay. The sort of industry standard, okay, is to do these fairly involved so-called short-shoal stellar orbit modeling in order to sort of tease out the black hole mass. Okay, I won't go into the details, but this by itself is just a sort of a very parallel supercomputer calculation you can do within a few hours for each galaxy. It's not too expensive since it's so parallel. And basically, the basic idea is we assume some stellar is equilibrium static potential. Okay, and we assume the density has a black hole at the center, some light profile, and there are two parameters: the black hole mass we would like to constrain, and the stellar mass to light ratio, which multiplies the luminosity density, and then the dark matter halo. Okay, and we generate tens and tens of thousands of allowed orbits for a given set of parameter, and you apply observational constraints. And the two major constraints, obviously, we're using are the one I mentioned, the line of sight velocity distribution we obtain from the spectra for all the parts of the galaxy, each galaxy. And then, of course, very importantly, you will allow whatever superposition of all the orbits you have for the stars to reproduce the observed light profile. Okay. So these are applied as a constraint to find out what's the best set of orbits that will reproduce the data. And then we vary. We just repeat this process for a grid in this two-dimensional space, and we find the chi-square contours. So to just show you an example of a result we get, and this is one of the record breaker, one of the two 10 billion solar mass black holes we reported last December, NGC 3842. So we get a contour by using our spectra kinematics, and by running the short-shoal orbit code, we're able to constrain. So this is how we got these numbers in the papers. Say it again? Let's see. It's probably normalized in some way. I mean, we can. It's a 1 sigma contour here. Okay, so we have 4 detections, 1 upper limit. So they contribute. So this is our sort of new compilation, okay, for the M black hole sigma relation. Okay, so here, like in the Göttingen paper, we color coded the galaxies by late type in blue, and early types are the red and green points. But here we just to highlight BCGs, we were curious to know if BCGs are different animals. We color coded BCGs by green. Okay, and the different symbols denote the 3 different major ways of getting kinematics based on stars, which is what we do, and which is believed to be somewhat more reliable than gas kinematics. But of course, the best things are masers. And what also make our compilation, our data set different from the Göttingen sample here, in addition to our new points, are these very important sort of 8 new maser measurements from Jenny Green and her NRAO collaborators that added a lot of the triangles here are new maser points, and they tended to be in this lower mass galaxies. Okay, and a number of them have been remodeled by Carl Gebhardt and collaborators, including dark matter halos and so on. So there's about half of the Göttingen points have been changed, and there have been new additions too. So if we just follow the industry's practice, okay, fitting just a power law to everybody, okay, for comparison, then this is the new beta is the slope, 5.48 that we obtained. Okay. But I would like to advocate in this talk that perhaps the community should move, especially theorists who are building models trying to explore black hole and galaxy growth, that I think it's time to move beyond this very naive global fit. And the reason being, if you break the galaxies into the red, the early type, red plus green, or the late types, you can see the fit. We got actually very comparable slopes, about 5. Okay? So you can see the red and the blue lines are parallel. But there is a significant offset, about a factor of 2 at a given sigma. So the early type, the black holes in early type galaxies are about a factor of 2, about 0.3 dec more massive than in the late types. Okay. So 5.4a really is just the combination of the fact that the late types have lower amplitude here, and they tend to live in the smaller sigma regime. So you combine these all together, of course, the global fit would like to be steeper. Okay? But I would like to advocate that people who build, after all, early type galaxies and late type galaxies are formed very differently. So if you want to sort of constrain your models, I think it's more interesting to look at the separate slopes and the amplitudes, and that's the current numbers we get, and it will be interesting to see if the theoretical models can reproduce these. Okay. And this epsilon 0 here indicates the intrinsic scatter in the relation, and like everybody, we're getting about 0.3 to 0.4, the intrinsic scatter. I'll return to that in a second. Okay, the intrinsic scatter is not very different for different types. One thing we try to do, the statistics are not very good, but we did attempt to break the 46 early types into whatever the core versus power law that I showed you earlier, based on the very inner light profile of these early type galaxies. And as I mentioned earlier, the core galaxies tended to be more luminous, more massive. Okay, so we were wondering if they have somewhat different fit. And you can see if I just draw these two lines through the data point, you will see that the core galaxies are somewhat steeper with a higher amplitude, but the error bars are very big. There are only so few points. So I think that's why I think we would like to really increase the sample by observing many more galaxies, especially the massive ellipticals. So another comparison I would like to just make is back to the global fit to all the galaxies. Okay, one thing one could do is to add upper limits on black holes. There have been a number of attempts. Every time you try to measure a black hole, you may not get it. Like 1 out of our 5, there's just not good enough data, but we were able to put an upper limit. So there are about 92 upper limits in the literature. Okay, so you can fit fold this into your fits using fancier statistics, but anyway, you can do it. The bottom line is within 1 sigma error bar, it's a little shallower, but still 5-ish. Okay, so adding upper limits doesn't change the slope too much. Another thing I would like to point out here is sigma. Okay, so we look at M sigma relation, and so much energy, effort, attention have been paid to the y-axis. How to measure the black hole mass, the error bars, and so on. And we seem to have taken sigma as granted. Now that we're starting to look at data, I just realized, wait a minute, what is sigma for a galaxy? Okay, in particular, now we have IFU data. So we have spatial information about sigma, and it's not flat, it's not uniform. Okay, so what sigma should we use when we plot M sigma relation? Okay. So there are 2 ways we explored. One is just light average, use luminosity average sigma from the central point to R effective. This is probably somewhat analogous to what sigma had been obtained in the lower, in the seeing limited observations. However, we have also tried, since we have much better resolution, angular resolution, so we have also tried by computing sigma by carving out, excluding the region within the sphere of influence of the black hole, in the attempt of getting a sigma that's not sort of affected by the black hole. So you can have a sort of more global representative measure of the galaxy bulges kinematics. Okay, so that tended to lower the sigma if you exclude the central region, because sigma tended to rise toward the black hole. And it could have a 15 to 20% effect. Okay, so these numbers we quoted are 9 of these, we have good enough data that we were able to compute sigma by excluding the sphere of influence. And that went into this. So we attempted to redo the fit by using sort of the more, traditional sigma that includes all the spatial information. And you can see, this tells you, it gets a little flatter because here the sigmas tended to move toward the left a little bit because they get smaller, so the slope goes up a little more. But here, it's not a dramatic change, but I think it's good to keep in mind what to use in the future. Okay, when we quote sigma, we should be a little bit more careful, and model builders should think about this too. And again, just to compare with Göttingen, it's a lot steeper, our slope. Okay, and we also have M luminosity relation and M black hole and bulge relation. I don't want to go into details here, but we are preparing this paper. We're about ready to submit it. Okay, but one last thing I would just want to emphasize is in the scatter of the relation. Okay, not just the mean trend, but the scatter. So here we do the very simple-minded thing. We have whatever galaxies we have, we broke them into equal number into 4 bins in sigma. Okay, just to show that, and just look at the intrinsic scatter here. Okay, basically, our point here is there is no obvious trend in the scatter in the black hole mass as a function of sigma. Now, this is actually quite important because there have been a number of recent theoretical papers that try to explain M sigma, or in particular M bulge relation. Okay, they claim that you can start out with a random, no correlation in M bulge and M black hole, but through mergers, the central limit theorem tended to wash out the outliers, and they show that their relation, the scatter, gets smaller and smaller at the higher end. We want to just say the data do not support this trend. Okay, so I think this is useful in constraining some of the merger-based models. Okay, so this is what I showed you earlier, that we're analyzing, we have reported these, and we're analyzing these, and we also have incoming data. We've been able to obtain quite a bit of a GMOS time, both south and north. And of course, this is the column we would like to get, but to give an indication of what they could be, we could use our best fit M sigma ML relation, and using the galaxy sigma and L, which are of course known, they're famous galaxies, and see what the predicted black hole mass is. As you can see, for some galaxies, they're very similar, okay, but some galaxies, they're off by a factor of 10. So it's good to, I think, to actually get dynamical measurements of the black hole mass directly, rather than relying on sigma or L as proxies. Okay, and since the field the data have been coming in quite rapidly in the past 3 years, and we're getting kind of tired of looking up all these different data, so we thought it would be nice to actually have a website, at least just for myself. It's just getting very confusing. So we are now trying, it takes a lot of time to learn how to do HTML, and this is really annoying. Yeah, but we have a really smart high school student who's helping us out, fortunately. And this is our tentative, we grabbed this .org, but if you know how to get, so I looked up, I would really like to get blackhole.org. And it says, this site could be for sale. I thought, I don't want to give them my credit card number yet. So if you know the politics of websites, let me know. Okay, but we are going to release this along with our paper that we'll submit next week. Okay, so in summary, I think it's time for the black hole community to actually have a central data site, and so that could include whatever new data points that come in. And ground-based big telescopes with IFU and AO make it feasible to now get black hole masses at the very, very massive end, which these galaxies tended to be more distant. Okay, and we've found a couple 10 billion solar mass black holes that could compete with the most massive quasars at high redshift. So that's tantalizing that these ellipticals could be remnants of the high redshift quasars. And again, we can now look at scaling relations, not just for this sort of naive global fit, but to look at subtypes. I think this will inform the theories much more clearly. And then again, the M sigma relation, everybody talks about what is the sigma? I mean, which sigma would you like to include, and how to measure it? And very important, lastly, the scatter does not increase, in the black hole mass does not increase at high end. We just don't see that. Thank you.